I'd like you to welcome Heather Stern. She is the presenter tonight, and she's going to be talking to us about frame buffers, and I guess we'll see what she has to say. Heather, take it away.
Glad to. So, given that in the last couple of weeks, Daniel was presenting to us some stuff about a particular video card driver, and the idea of getting a video card driver working in his kernel, and then actually posting the kernel change that he had made to the open source community, I figured that it would be fun to continue in the realm of the video space, but to focus on something that we might be a little more familiar with. I mean, almost everybody has a monitor which has some stupid sticker on its box somewhere that says that it's a VESA compliant monitor. And on the one hand, you might wonder what that even means, and on the other hand, you know that that means that at least when you plug it in, it's going to be able to see its text on the screen. Why is that? Because maybe you've got a frame buffer driver in your Linux kernel. So VESA is a standard, one of those committee type things where they put together a table of information about these exact frequencies should be supported. If you're at this resolution and you do this frequency, it's normal, and you should handle it in this fashion. That allowed a lot of manufacturers of monitors to be able to produce monitors that all said that they'd work with your video card. It allowed a lot of video card manufacturers to say that they could all support all your big pile of monitors without having to know what the other monitor was. It was a big advantage for the community as well because we could run out and buy cheaper monitors. But how is it that it really decides this and does it for us? So here we see a structure that's been defined, and that's very similar to the structures that Daniel was presenting to us before. Just a few things. You could see a right margin, an upper margin, and a lower margin. Just what these values mean may not be totally clear. They probably relate to this screeninfo.h file that we saw further up as an inclusion. There's another structure of the same type. So if you get to wandering around the kernel sources, even of other types, get used to seeing a structure where these values that equal some sort of string variable, or possibly a numeric variable. And don't be too surprised if one of these word value things here is actually a list of almost a table of numbers from one of these .h files. So here we're declaring a batch of ints that's going to be read. I kind of like this one, read mostly. I'm sure that that means something quite amusing to the programmers who are going through this.
Actually, Heather, I can explain what that and Anit Data mean if you want.
Grab the mic.
Great idea. Oh.
Jim's going to comment on read mostly.
So yeah. So what the programmers are doing here is they've got a couple of, and I don't remember exactly how it's implemented, but they've got a couple of special compiler directives which basically are hints to the optimizer, in this case read mostly, to say that this value is something which is usually just being read, rarely being written to. That allows it to optimize how it lays this thing out in memory. The Anit Data thing is another little trick that they do because it declares it to be in a special ELF header. So the kernel, of course, is compiled actually as an ELF formatted executable, even though, oddly enough, it's the thing that executes all of the rest of ELF. But one of the tricks is that after the kernel has initialized itself, then it has a mechanism for throwing away all of the stuff that was marked in the section named Anit Data. This allows it, if you've ever very carefully looked at your dmessage or at your startup messages when the kernel is booting, you'll see a message somewhere in there, 576 kilobytes freed. That's all the init data that it threw away because it only needs it while it's initializing the system and doing all that auto detection and auto configuration. Once that's done, it gets to throw all that away and use that as regular memory. So that's what those are. They're weird hacks that hints, hacks, they're special tricks in using the compiler and the linkers to tell it how to do things a little differently.
So at this location, it's talking about an offset, and I believe that's an offset into memory for the way that it's handling the video page. It's saying down here offset, and it's bit shifting at 16, and these values E something X, those are register values. So this is using the registers of the 386 in order to get the effects that it wants. VESA set palette. VESA spec is red, green, blue calculation, so this sets up the red, green, blue stuff. And it's going to try all the nice VGA stuff that was standardized before the SVGA-based VESA pattern goes. Hey, John.
Hello. Oh, now we can start.
Okay, it's official.
And what it calls falling back. This is a different way for it to get at the red, green, blue so that it knows it can get that. Again, we see the E something X registers and its ability to set the palette. Otherwise, it can't do that, and it should return. And there's the color registers. So a lot of this, by the time you've gotten down here, feels the same. Okay, more red, green, blue stuff. We're all good. And these cases, notice how these cases are actually divisible by 8. That's pretty much because of the offset of the values of the colors. And you can see the red and the green and the blue offset down here at the bottom right now. The other frame buffers actually have some similar characteristics. So before I slide down too far in this, I'm going to open up one of the other ones so you can see. Let's see the And the source I had been looking at previously, the Intel frame buffer stuff, was actually at the top. So this might end up looking a slight bit different than the one I was looking at, but I'll go here into the Intel one. I expect this one to be a little unusual because the Intel family of chipsets are actually shared memory kind of things. So they're not actually using memory that's on the video card. They're using logic that's on the video card to do video things, but they're using memory provided by the system. So I expect to see a bunch of the structures about color registers be the same, but some of the stuff about allocation to look a little different. Allocate for panning. Preferred mode. Notice that 70 hertz. That might be pretty popular on your monitors, but the guys in the back on the projector stuff would have been a little unhappy and want to try and get it down to 60. All these IDs for the supported devices, if you were going to do what Daniel had to do last week, you might be in here messing with adding another value for yet another supported device. If you're looking at the register size there and it was a new device, it might actually have some slightly more size, although on the other hand, there's a bunch of different supported models in here, so that probably would not need to be messed with. Defining a few macros for some basic math so that when we're looking at the stuff later down, it can be easier to read. round down to page and things like that. A bunch of stuff about video is going to look like a bunch of strange math, which is why it's really handy to get things switched to words as soon as they could get it. So there's a ring buffer size for the video stuff and a cursor size. So by that kind of cursor, I believe that they mean the text-based cursor that you see on a text-based screen.
Is this all 24-bit video?
Well, in this case, I'm in the Intel framebuffer code. So it's almost certain not to be 32-bit.
Okay, but sometimes there's 16-bit.
If it's going to stick to the VESA standard, which we were at in the previous one, I'd be pretty certain that it would stay at 16-bit unless you forced it with one of these true color aspects. So in this one, we have it doing a quick calculation to decide how much video memory to use up. And it just being fairly possible to reuse values we've already gotten calculated allows it to load up faster. So down here, it's complaining that it can't reserve some video memory. We can't make this fatal because actually, I mean, I don't think that the comment's very fair. It says sometimes this comes from magic spaces we don't know about. It's also true that the way that we are going to use Linux, we might not care if the video actually works. We might want it to fall back to switching to a console driver. We might decide it's okay if the frame buffer doesn't work. The thing that had originally gotten me interested in looking at the VESA frame buffer driver, which is why I have any experience with this driver at all, is that I had this wonderful, beautiful, lots of memory video card, and I had this beautiful, incredibly gorgeous 22-inch monitor. Or is it 23? I don't know. It's got 1.5 inch bezels. This is like, I'm not going to sit there with a measuring thing going, is it 1 inch longer? Should I be unhappy with it? No, it's big. It's gorgeous. I should love it. But if I fed it this wonderful video card and I just told it, sure, go ahead and text, you know, I'm going to be in graphic mode in a moment when I run X11, I couldn't see anything in the text mode world, which means I couldn't go and configure all my little text files so things would come up gorgeous like I wanted. I wanted to be able to see what I was doing. And the graphic mode, once it came up, like GDM was automatically installed by my distribution, that part worked fine. So I'm like, okay, I guess it really wants to be in beautiful graphics mode, even if it's doing text. So I needed to get a frame buffer. And we have a bunch of messages here about where it successfully reserves the frame buffer. I don't know if any of you guys have any interest in how memory mapping works. Mostly I didn't. I just wanted to see how far I could get along till I could get to those tables to see, oh, this is 1024 by 768. This is 1280 by 10 something or other, 1060 I think it was. I wanted to be able to see if I could sneak in that extra video mode that was that beautiful 22-inch HD TV kind of look about it. I figured if I couldn't succeed, oh well, but I wanted to see if I could do it.
Do you know if this driver works with AMD64? Is it 64-bit compatible?
Well, my AMD 64 at home doesn't have any problem doing graphics, but I'm not sure if it's using the VESA frame buffer driver or not. In a strictly speaking sense, this driver doesn't care about your CPU. This driver cares about your GPU.
Yeah.
And as long as whatever it was that you were doing did that if def under 386 under, then you would get the values that went with that portion. Now, if it was setting that and those weren't valid, then you'll have a little discussion with the people who coded that section. Or you'd have a little discussion with your C compiler and see if you could code up that section till it behaved itself. And you'd actually have something to discuss with them, like, hey, if I patch it like this, then it works, at least for that. Of course, I don't know if it fails for a dozen other people now. Now here's an interesting message. Memory area is not supported yet. We have to set up a descriptor for the requested memory area and pass it in this register to the BIOS function. So we are actually using stuff that's on the motherboard. Once we decided we think we got some values, we have to tell the motherboard back that we were using these values so it'll do the right thing. And that's setting the palette.
Well, that means
In this case, it got some sort of response that didn't work out. It's like, well, sorry, too bad. Hardware palette's unchangeable. Yes, yes, John?
that means that.
Microphone?
Oh, sorry. That means that there's a switch back into real mode or virtual x86 mode inside the Linux kernel.
I think, strictly speaking, we're actually communicating with something that is in real mode still, so that there might be a mix of pieces. So we probably have memory mapped this into a section of code that's living in its own little box. We got to tell the BIOS something, and then if we don't care that it got its answer or not, we might not actually care to jump back to real mode.
Microphone?
Are you still actually in an underscore init function? Up near the top of this, I saw a function defined as under init. I don't know. Well, you'll.
Nope, we're inside a.
Yeah, I
yes, we
see
are.
under init.
Under init.
So you're
Basic
still in real
FP
mode.
Setup. We're still in real mode anyway, so we're not switching anything.
This is just initialization stuff. It'll get thrown away later.
Okay.
Can't handle memory requests of a certain sort. Scrolling using protected mode interface. So I think that as we continue along here, we're really going through the BIOS, asking it a bunch of things about the features it's going to be able to offer us, and then setting up things that we need along the way, so that when we leave this real mode interface, we're not going to have to come back for it. So there's our red, position and size, green, position and size, blue, and what's this RSVD thingy? Well, it's transpa, so that is almost certainly supposed to be really short for the word reserved. There's our bits per pixel setting. If it's less than 8, then we could do all this simple stuff. We might have just asked for something that already exists, so that's cool. There's an option in the kernel sources when you're actually going through the config interface and you can check things off. Hey, are we supposed to get MTRRs? This is a special kind of register that a lot of the video apps like to use to check back into things. So if you can provide these, it actually does make things a lot faster. So I do recommend checking that off if you're building a kernel and you can do that. Then it's usually already checked, because when you're looking at a kernel source and you're going through the checkboxes, you notice a lot of things are checked off. That's usually because the guy who's the current maintainer of that particular flavor of the kernel, he had to check that off to make his box work. Or he preferred to check that off to make his box do nice things.
Check off?
Well,
No Star Trek jokes.
he puts a little X in the space box, or he checks, well, I mean, how many people here use a GUI interface to compile their kernels? I'm not raising my hand.
It's faster. Erasing.
Yeah.
Well, the real reason I don't is because,
You mean in make menu config?
yeah, the real reason I don't is because I want to dive into every little option reading its little help file, because that's how I learn more about the kernel.
So did you already define MTRR? memory type region register.
Well, I'm just actually looking at the source code here. I'm not trying to compile anything.
Okay.
No, she had not explained what it means.
Is that important? If it's not important, move on.
We set the value of the size for this thing, and then there's the end of that section. If we didn't need it, we don't have a size for it. There's another one of those little structures. Some value equals a thing. And here we are at the end of the init. The portion above this section will be let go as soon as we move on to the other stuff. But we've got this platform device. We're registering as this kind of driver. So that means that the rest of the kernel is going to know when we need this kind of service, this is the code to call. And right here at the bottom, the module license is a GPL, which means that it's a fully registered driver. It's not going to cause all the kernel people when you send them a message about it to say, you're using some sort of off-brand kind of thing. We're just not going to deal with you. Jumping down to here, I don't see anything about GPL in this one, but it's probably in there somewhere. This might not actually be the top of its code block for its section because there were a bunch of other files in that portion. But here's an example of a bunch of those variables set that are all the same kind of thing. They're sort of a table, but they're really not. Again, you'll see a lot of that in a bunch of these pieces of code. Analog, DVO, SDVO. I don't know why they say DVO instead of SVideo, but I'm guessing that that's SVideo. Unfortunately, I'm not a TV geek, so a lot of the TV capture stuff wasn't all that specific to things in my brain, but I think a couple of these values probably would have been useful for that. There's all those Intel chipsets. And here's a billion zillion variables that have to do with all the cool things it's going to do a little later in this block of code. You've heard of that AGP stuff? How many of you know what the AGP is supposed to be good for? John and Bruce. Bruce, would you like to comment on it?
Video cards.
AGP. Yes. AGP stands for Advanced Graphics Port, and it's a variation of the PCI standard that allows you to, because it's a much shorter bus, to have a much higher bandwidth to graphics memory.
Which allows graphical memory to be used much more quickly than the rest of the stuff, which allows your video to look like it's going at a nice speedy pace, which means when your computer is crunching its little brains out trying to decide if you've been shot by the creatures in Quake or whatever it is going on right now, that you're getting a chance to actually see all the beautiful flames in the background and they're really moving and stuff.
And isn't it been superseded by PCI Express and PCI-X? I'll let her repeat the question.
I'm being asked if the AGP bus has been superseded by things like PCI Express. It comes in PCIe and PCI-X and has all these really weird-looking slots that look slightly different. The AGP appears to be about how fast the bits are pushed. It's sort of like how many can be crammed in and shipped around. And the card stuff seems to be about access to other pieces of memory. I'm not entirely sure.
It sounds like what you're suggesting is that the fact that a lot of the code refers to AGP is sort of an artifact of the original AGP hardware, and although the hardware is no longer called AGP, some of the interfaces to it for the software are similar enough that the code can still work with it.
Yes.
So that's why you're going to see it in a lot of the
API
source code.
To the software may actually be making a point of using the same structures so that the programmers don't need to remap their life just because the hardware designers were able to tighten things up. We have a hardware cursor on this type of video card. That means that in this particular frame buffer mode, the little arrow or little line or dot that is on a screen that indicates where the actual input activity is going on is something that's driven by the hardware. So some piece of software could just say, move the cursor to that other point. It doesn't have to actually waste a bunch of time in code on telling it how to paint a cursor. On the other hand, it does mean that if something's blinking its little cursor, it might really be stuck, but the video hardware might still be handling how to make the little blinky line do blinky line things. This thing about accelerated is a value about whether it's got some code that's very specific to that particular type of hardware. And I suspect in this case of this driver, that's going to be yes.
What's the actual driver comment of that?
I am in Intel FB.h right now in the subdirectory Intel FB under video, under drivers,
Linux drivers.
under the Linux kernel source for this particular kernel source. I think any one of the later 2.6s is going to have this structure in it. I know that the Intel frame buffer itself has been around for a while. So even in a much earlier kernel, it might not be a subdirectory with 5 or 6 moving parts kind of files in it, but it would be in there.
FB.c or something like that. I don't know.
Well,
It's the actual .c.
it's that Intel FB. Linux 2.6 drivers, video, Intel FB, Intel FB.h. The unfortunate thing is when you get your driver sources, when you get your kernel sources from a particular distribution, you might only get it for some portion of the activity it thinks that you would want to look at instead of all of it. When you get it as a tarball from kernel.org, you get it for basically every architecture you could think of. You might even want to cross-compile it for one of the other types. And it's not going to prevent you from doing that. It gives you an opportunity to look into, say, the frame buffer from the Spark kernels or the frame buffer from one of the other platforms. And to do things like we're doing here. There are a lot of FB-type kernels. Each one of these that is some sort of strange thing or other and ends in FB has some specialized code relating to that particular video card. And almost certainly near the top has a bunch of includes that refer to the stuff that is more generic and shared by all frame buffers.
Wow, that's a nice collection.
Quite. It needs to only be like 7 or 8 of these.
Ooh, they even have the SGI frame buffer.
That's true. I'd say a bunch of these cards I don't even recognize. I didn't know they had specialty frame buffers for those. But Trident frame buffer's been around for a long time because Trident's always been weird. It's never been quite basic. Does anyone have any questions that might lead a direction that you'd like me to dive into next to going around with this?
Well, I did want to come back to the question of... Oh, yeah. We'll talk on the microphone. So I did want to come back to the question that this is all under init under real mode.
Yes.
So...
The frame buffer would be one of the earliest drivers loaded because it would be in charge of making sure that you could see what you were doing. It probably actually loads even before that logo that shows you the cute little penguins.
Yes, but the thing that I'm going to get to next is that this code is generated especially because in normal real mode, integers are 16 bits, and it looks like a lot of what I saw up there was 32-bit integers. So there's a flag being passed to the make file which says treat integers as 32, even though we're in real mode.
Is it all actually real mode, even though some of these are modules that can be loaded after the fact? I mean,
I think that some of the initialization portion is real mode, and as soon as it possibly can escape to it, it jumps to protected mode.
okay, so like the initial VGA stuff that's common to all the cards is going to be initialized in that real mode.
Right. It's going to check a bunch of raw features about the BIOS, scoop them up into some registers, and then bail on it and move up.
Okay.
I think if you looked in those. So all of the actual functions that declare themselves as under init are the ones that will be eligible to be thrown away. The various structures and things that are defined with under init data are in a separate section, which is data, which can be then thrown away. But these files can contain a variety of structures and functions which are not marked that way. And those are the ones that will be kept in the module or in the kernel if you're linking it directly in, and be used by the kernel during, when it's in protected mode and doing its thing. It's a little more complicated than that, but if we went through these, now, probably the best bet would also be at some point to provide an overview of how the frame buffer works, because there's a minimal amount of functionality that shifts the modes and that sets up the mappings, but the frame buffer is basically a block device. That's how you access it. So if you could, Heather, do you have an explanation of a high-level explanation of how the frame buffer works?
Well, basically,
from user space's point of view?
Sure. Basically, an area of memory has been set aside to be fiddled with by the driver and treated as if it's the video card so that things can be done a little faster. And there's this interface that's really nice and smoothed down that can be used to communicate with it quickly. Therefore, things can be prepared ahead of time from the application point of view, and can be blitted into place right away. Or some of the, I'm using blitting as an example, but one or another of the video features can be invoked right away, which means that its ability to show up on the screen feels really fast. Especially it feels really fast if that frame buffer has been really tuned to how that hardware correctly works, so the underlying command is really the correct command and not just some sort of little crackerjack box about kind of sort of working.
Can you go into FB.H?
Now, I was just saying that here's a VGA 16 frame buffer driver, and we were looking at the top of the frame buffer driver code for the VESA one before, and in this case, we see an awful lot of them that are exactly the same, so the obvious ones to take a look at to see some more of what's going on behind the brain of this is Linux FB.H and maybe this screen_info.h. By Linux, it means not in the driver's directory here, and not at the very top of the thing, but inside the include directory, there is a Linux area. And in here is that fb.h.
Right, that's the bracket include instead of quoted.
So it has set aside a certain number of frame buffers. If you were doing some really heavy graphics processing and doing something strange, you might be changing the value on that maximum to use up a bunch more memory, so you'd have a bunch more frame buffers used to do something strange with them.
FB major is the device major number.
Yeah, you would not normally want to mess with the device major number.
Heather, could you, sufficient for now, what is that?
The device major number?
Okay, but.
Sufficient for now. How many frame buffers do you want? 2? 7? Oh, that might not be very many. How about 32? That's a good round 8-bit kind of number.
Basically, that's a hint of the number of minor numbers that they will allocate within that major number, so that they could distinguish about how many possible frame buffer devices could you have running on a single machine concurrently. 32? That's a lot.
I certainly hope that's a lot, but if you're doing something really strange and graphic-y, maybe you would need more for some reason.
I think the programmer was having a sense of humor.
Yes, he
It's his comment.
Okay.
All right.
So do you understand the concept of major and minor numbers in a generic way? Okay.
Anyone else want me to comment further on major and minor numbers within a device?
Actually, why don't you go look at the actual devices in ls-l of the device nodes within.
Still disturbing to see comments like that.
Those probably aren't it.
Something FB, RFB star.
Well, we're not using, well, I don't know if we're using a frame buffer on this particular setup.
Well,
It might
you should
be.
still have the devices, or is this UDEV? It's UDEV.
Hey, I might do DevFS on a different one, UDev, whatever it is, but I think that's a deeper exploration. We probably want to start with simple stuff first.
Connected with that or not? Yes, you are. You could,
Base of levels, base of funny little values. The reason a bunch of these things are hex values is because they're going to be crammed into little variable registers or variables that are used for other things. Anyway, the whole point is to get them turned into words so you can make sense out of them. So here we are at packed pixels and interleaved planes and non-interleaved planes. You could basically say, hey, which kind of attribute am I messing with right now? This one. Like that true color everybody's really fond of. Pseudocolor read-only versus regular pseudocolor. You know, I haven't ever had any circumstance to dive into how those would behave any differently. But I'm supposing that if it's read-only, that you wouldn't have an opportunity to easily tell the video card you want to change something just a little bit. You would have to actually tell it you want to refresh the whole thing, and it would be much slower.
So these Linux drivers support 8, 16, and 24-bit color. Do they support 32-bit color?
That might depend on the video card and therefore the exact frame buffer driver you were looking at.
Are you aware of any of them that support 32-bit color?
I know some of them that I was looking at that said they supported true color, and then when I dove into it, I realized that they meant that for their context, true meant 24 after all.
Okay.
They were doing some sort of additional juggling to get the 32-bit behavior, but they were sort of leaving some colors off the other end when they did it. They were just taking advantage of the fact that their code was really fast to make it feel like it.
32 is not more colors.
It was just commented that 32 bits is not more colors. Is it the alpha channel? Is that what? So Daniel was referring to the fact that the 8 bits that you gain from 32-bit are actually used for alpha channel, which is the opacity of the color.
The main use of the alpha channel is so that you can do really cool things with either
Transparency.
with when you're using a window manager in X somewhere and you got a bunch of like X terms with these apparently not quite opaque screens, so they can see pieces of the background wallpaper behind it, or they can see pieces of their fellow terminal windows behind it. Many of the window managers can do some sort of fake, almost looks like the background is showing through kind of things, where they're actually copying the background forward. But if you really have good alpha channels, you would be able to look at you would have these pieces of video able to look at the other things that have been buffered and show them actually passing through. So you would be able to see a terminal window partly obscuring another terminal window, and if there was flowing text on it, you would be able to see it flowing correctly.
As if they were color filters laid over each other, or
Yes.
something like that.
Exactly so. Popular color shades would be dark green for one of them and a black or a midnight blue for another one. At maybe 80–85% opacity.
If you'd like to, you can show a fake opacity on that. If you go up to settings, it has it under the, it has it in there if you want to show off that effect, but I'm not sure if that's useful.
In the case of the wallpaper that's on here, I'm not sure you would actually get a really cool looking effect.
I put top, back.
This one, this isn't actually composite.
Now, remember that the file we're looking at here is actually the fb.h that's included by a lot of them. So it starts out, it also has these named values for, maybe there's not a hardware accelerator, maybe there's all this, that, or the other thing, so that later in the buffer drivers, they can refer to themselves by name. Kind of, sort of. You know, I'm a 57th type of video card or whatever. And more of these structures for them to keep little names of things or flags on and off whether something is turned on or not. Reserved for future compatibility. Or an opportunity to anger some hardware driver because they went and reserved it for themselves and did something futuristic with it, and then you went and did something else futuristic. The offset for the color fields. So any sort of bit field you might use for something is going to, you can use and reuse this structure type.
So just as a side comment, 24-bit color is normally pretty good, and it's better than your TV set most of the time, much better than your TV set. But high-quality professional film will render 42-bit color. So, you know, 24, pretty awesome most of the time, but, you know, if you really want the good stuff, then you have a much more expensive display.
There's more than one reason that a video monitor attached to a computer is going to feel like it's much better than your television display. One of those is that a really old-fashioned style CRT video display has all these pixels. This one spot of color, whatever color it's going to be, is actually itself made of multiple parts, and that's the origin of this whole RGB thing in the first place. There's a red gun back there and a green gun back there and a blue gun back there passing their value through a grid, and the grid's either electrically activated or it's not to let that signal through, and you get, so that's how you get these spots. But the pixel is so big you can see it if you want to like sort of stare at the screen really quick.
Okay,
It's
so
pretty gritty.
Interlaced versus non-interlaced.
Whereas
And
if you've seen,
standing for never the same color twice or something?
Yeah, never
Never
twice
twice the same color. Right. So
the same color.
to repeat, it's been commented that NTSC stands for never twice the same color. If you've, on the other hand, seen a modern LCD either on a laptop or one of these beautiful flat panel monitors in front of your computer and a pixel's out, and you switch it to a black console mode and the pixel's still out and it's bright as bright can be, you can see what size a pixel is. Man, it's barely a dot. Yeah, it's a pinhead. Well, okay, maybe it's the head size of the head side of the pinhead rather than the point side of the pinhead for what size it is. That's pretty tiny. It's a lot tinier than you see on a gritty old CRT television screen. And the combination of a lot tinier dots plus what feels like a lot more colors, even if it really adds up to about the same colors, feels like this brilliant photo quality kind of stuff. It doesn't quite measure up to true film quality if you're using the right kind of film, because the film is actually an analog emulsification and is showing you however much light it got transmitted into it to activate the colors in that film. Turning that into a digital form is going to try to, the people who are working with photos are going to try to produce as many bits into their color as they possibly can. They're doing their best to preserve that analog feeling. So there are a huge number of these beautiful file formats. Targa, I think, was one of the early ones.
Yes, I'm just trying to make a connection in people's mind. It's because if they look at their scanner will say it'll generate 48-bit color, right? And then we're talking about 8, 16, and 24-bit color on their monitor. And so there is a potential loss of color resolution as you go from your scanner to your display. That's the only thing that I'm really trying to point out.
That's true. Some of these behaviors of a frame buffer, these are features that a video card might be able to do or not do. It might be able to do something to all of the buffers that you've set aside for your video at once, or it might be able to hold off some sort of material for some action you've called for. These are just the bits that are naming the request you're about to try to make. Most of the traits here that we're describing are stuff about how TVs and monitors work. Sync on Green is a really old style of monitor. I got one at home. I could probably sell it on Craigslist for some good money. How many of you are familiar with video interlacing?
Maybe I versus maybe B.
If the interlacing is really slow, you can actually see all the even lines fill in before the odd ones come back. And the advantage of doing some buffering would be that the interlacing could happen fast enough that your eye might not as easily be able to spot it. The current standard for cheap film for television use is about 30 frames a second. You would want a lot faster if you wanted it to feel lifelike and realistic.
30 frames interlaced, right?
Yeah. The frame buffers can be set to handle the grayscales as well as the colors. 256 grays is considered a lot of gray. And there's those margins we saw before all over again. That pixel clock is the heartbeat of a video card. And you'll find it referred to in the X11 config files near the beginning of the mode line. The pixel clock, the video is sort of the timing by which the video card and the monitor are going to pass commands to each other. Video memory is actually normally able to flow its information both ways, because that's what makes video feel fast. So video memory is much more expensive than ordinary memory because of the way it's got its ports lined up. I think by blanked here they mean that the monitor is actually being told to clear some values for itself before it does something.
Oh. Blanking, this is an AIK, all right? The blanking is when you've got.
We got a microphone.
Pass the microphone to Paul here.
If you've got an image that's already been rendered on the monitor and you're about to replace that line with another line, a blanking pass would clear that entire line and then you write into it, whereas a non-blanking pass is one where you're just writing new data and the old data is, do you
Still
see
there.
the difference? Instead of taking the entire line and blacking it and then putting your bits down.
Right, maybe you only want to
That's a
change
blanking pass.
a
And then the
little glint in
non-blanking
somebody's eye
pass
or
is you
something.
leave the other bits there and then make your pass. and write your bits. So and that starts to matter whenever you've got multiple passes per pixel and things like that can happen. So when it starts to matter whether or not you're doing blanking passes or not. It's just a
Certainly non-blanking would end up feeling like it was a more subtle change.
Yeah, and the thing is that some monitors can and can't handle the other way. So that's been at least that's my understanding. So we can move on.
So
that may be total horseshit.
I find it a little odd that the comments here.
Oops, sorry.
I find it a little odd that the programmer's comments here refer to HSync and VSync when in other documentation about video programming, the vertical is nearly always referred to as refresh. That the horizontal signal synchronizes and the vertical signal refreshes. But from our human standpoint, it really is the same thing, so. The current scanning position, scan line and scan dot position, in a graphic sense, you can think of that as the current cursor point where it's about to make a change in the video. There's another one of those pesky reserved for future compatibility things. It's only 4.
I kind of hope people realize that the reason for doing that, allocating a little bit of extra space at the end of certain structures, is because that will allow the entire structure to align itself on memory boundaries that will work more efficiently overall. So you're going to see a lot of that, just little bits of extra padding space at the end that currently isn't used by the structure, but just make sure it lines up correctly.
Doesn't the compiler pad the structure anyways?
Yes. I was wondering.
You always do it the way you want it to.
Okay.
They're ensuring it.
I'll repeat. It has been asked whether the compiler doesn't just pad the structure anyways. And yes, it should, but the question is whether it really does. A certain amount of defense of itself in the structure might be programmed in this fashion to mark it reserved so that it can't be messed with.
The other problem, I mean, not problem, but the other reason that it might be reserved is to be able to preserve like binary compatibility in the future, right? I mean, you might be able to add fields even in the case where the compiler adds, aligns it for you. This ensures that at least that much space is available. So when you make a change to the structure in the future, I'm sorry, go ahead.
I think it would also allow some room for, the VGA standard was put together a long time ago by some committee people after a bunch of people in the marketplace were putting together monitor cards that only kind of almost work together. And the VESA standard was much the same. They got together, they made a committee, they said, look, if you use these refresh rates and these values and these controls, you can have these dozens of other cool features, and people might like your card better than this other guy's card, or vice versa. But at least this way, some modes are going to work on most monitors, regardless if people could just go buy your cards and then fuss over the cool stuff additionally. In this case, let's say 2 years up the line from now, I mean, the VESA standard's been around a long time. A bunch of video card manufacturers might get together again and say, we got to have the 6400-bit standard and do all these other cool things that you couldn't do before GPUs got brilliant 1 gigahertz speeds or something. And that might provide a standard set of features which haven't been referred to in these frame buffer drivers right now. But there's some room to put a bit flag or something that says, go look at the additional cool stuff. There's even more cool stuff. Go look over there.
In this particular case, they might actually be in the VESA standard that they have to reserve those. I don't know.
And Jim notes that in this particular case, the VESA standard as presently written may require them to make sure that these spaces are there to reserve space for that concept.
So there's an additional reason why you have space, and that is that although this driver is not necessarily transportable,
This isn't a specific driver. This is a baseline file that all of the drivers that are frame buffer seem to include.
but the general need is that you want this file to also compile on multiple architectures. And so it's not just the Intel compiler or the Intel compatible compilers you want to do something with. It's all the cross-compiling and all the processor architectures you want to be compatible
Correct.
with.
The Spark frame buffer and the SGI frame buffer both also use this file. So we see more cases of these structures that just are, regardless of the fact that C is not particularly object-oriented language, if you create the structures and reuse them strongly enough and constantly, you can use them to build for yourself object-oriented styles of code. And so these very primitive structures can be used over and over for that kind of behavior. Reuse of code is good. It makes things nice and tight. And we like fast code when we're doing video stuff because people see it when it's too slow. So there's a frame buffer cursor. You get to see it. You get to tell it what it looks like. You get to tell it where the hotspot is among the little space that you've frame buffered off. Maybe it doesn't look like an arrow. Maybe it looks like a boat or whatever. Here's a bunch more includes. Well, let's see. We have a backlight. Ooh. And a work queue and a notifier. So there's all this stuff about probably how to handle an individual buffer at a time. So that frame buffering logic, however many buffers you've got, each one can be handled separately. In the parsed monitor specs. Now, you might wonder, what do you mean by parsed monitors? There's this protocol called EDID, which allows video cards or programs that are doing video stuff to ask the monitor, hey, what's your specs? And a properly basic compliant monitor is supposed to be able to answer in a format that the EDID portion of the spec actually covers. It's exactly, this is a mode that I handled, this is what its frequency is, and a bunch of these traits. And for a long time now, there have been apps either on the side or code fragments inside X11 servers that would be able to ask that monitor that trait.
It's waiting for you.
And that would be why X11, without a bunch of stuff in its config file, could auto-detect what your monitor does and still come up with usable video mode.
Of course, the fun thing is X was never actually designed prior to this version to be very dynamic. So they've just started adding features where when you plug in a monitor, it will redetect all of that. And some drivers cannot actually do the detection while in X yet. So that allows for fun things like plugging in a monitor and having it automatically expand your desktop over to it. So is EDID still used in DVI, or is there some other, or is that just wrapped into the DVI protocol?
I think there's some cases where it might fall back to that if it couldn't figure it out any of the cool modern ways.
Yeah.
I do know that I used to make quite a bit of money helping people set up really weird mode lines for their really weird monitors because, I mean, back before this got so standardized that every monitor was doing this, some of them just actually took advantage of the fact that the spec says, you can report back 0 and say, I don't know what my modes are, figure it out yourself.
Well, the fun part was I also had a friend with one of those gateway destination, 30-inch monitors back in the day, and the monitor would only run at 640 by 480 unless you keyed in the right frame buffer. I mean, not frame buffer, if you keyed in the right mode lines to it. So back in the day, that kind of stuff was very common, but now not so much.
And for monitors which were sufficiently primitive in the sense of auto-detection, you wouldn't have any idea what to feed it for the right mode lines unless you were you dug up the PDF of or the actual halfway Korean, halfway Japanglish, something or other worth of a manual, and we're reading things out of the table in the back.
Which is why they actually used to give that information.
So what was the part that you had to change to get your big Apple monitor? Some of the display.
Oh, yeah. The question he asked was, what was the part that I had to change to get my Apple monitor working? It wasn't actually that I had to change anything to get my Apple monitor working, but that I was curious where it kept the table of all of those nifty modes so that I could see if I could change it or add a line or two. And I wasn't sure at the time if that table was something that was shared among several video buffer drivers, or if it was something that was separately and strangely buried in each one. So in the case of the offending driver that I was fussing with, I had an ATI video card and a beautiful Apple Cinema display, which is not the current model anymore, obviously. And it turned out that what I was looking for, now this says ATA FB, and I think that means not quite the same thing I was looking for. I ended up looking at Radeon stuff. Where all the Radeon acceleration is. And I think I was in the 128. But let's take a look here, since this is newer kernel sources than I had originally done it on, and Radeon_monitor, and see if there's a nice little table of traits to tag on. Default res, and some pixel clock stuff, and a few length kind of things. If you're familiar with video card architecture, you know that there's something called a front porch and a back porch. What those things are really referring to is when they were working with CRTs, the swing of the video gun to one edge will go past the portion of the grid that could be electrified. So there was a portion where it was not worth sending gun signal, and there was a portion on the other end where it wasn't worth sending gun signal. So you had to have a timing for how long it took for the gun to swing all the way back to the other side so it could do another scan. In LCDs, you don't have that problem, but that allows it in order to still look like a monitor, it has these values anyway. It's just the porch is, for some reason, really, really tiny. So this contains some hacks to work around a few machine models with broken probing by hard-coding some known EDIDs from some naughty laptop internal panels. Well, we've never had to hack any video drivers, have we? So we spot your display type, and if your display type is one of the naughty ones, then we force feed it. And otherwise, we see if we can ask what its information is, and maybe we don't get a good answer. But here's how we go probing for it. Should I check for this value here? I need to check out what it does when booting with the lid closed. A Radeon mobility, so that it could see if it had to handle a laptop special. Oh, I couldn't do this thing with a panel. Hey, I found it in the BIOS table, really cool. I can do all these values with it. Connection type. Now this is interesting. I guess that this particular structure has to have a certain number of entries in it. And for all the entries that it's just not bothering to use, it marks them all with a magic string unknown. On here, on monitor layout string, this mostly is covered from XFree's Radeon driver. Oh, that looks pretty ignorable. Probe the display on both primary and secondary cards connector. If you have more than one video card in your machine, I think that it's going to end up using this code. Or if you have a dual-headed video card, it almost certainly has to use this code. So I don't know how many of you have heard of an I2C interface. Someone hand the mic to Daniel.
Pronounced I squared C.
I squared C. Well, it turns out that the Radeon frame buffer has support for that type of connection, which allows for, in this case, it's that DDC is some stuff about internal behavior for the video card. I think that's some internal tables that the card has for RAMDAC stuff.
Display data channel is what EDID travels over.
Display data channel is what the EDID information travels over. It's how it learns the information.
What's a reversed DAC? Could you repeat the question?
What I've been asked, what's a reverse DAC? Because this particular chunk of code refers to a reverse DAC, or controllers using BIOS. A DAC, go ahead, hand him the mic.
Well, DAC stands for digital analog converter, but a reverse DAC would be like an analog to digital converter, but they didn't say that, ADC.
No, I think that if you look at the code below, you see the right bit shifts. I don't know for sure, but if you look at the code below, you see the right bit shifts. I think that they expect them to be A, B, C, D, and write to them in that order, and sometimes you'll find them in the hardware as A, C, D, B.
Oh, it's the Lendian big Endian thing.
Is it?
Yeah.
Endian bitness in your pesky digital audio converter might make it a little hard for it to be converting in the right direction or doing the actually correct conversions.
So while we're on it, what's a TMDS?
What's a TMDS? Has been asked. TMDS is stuff that I haven't messed with, so maybe someone who plays deeper in the video magic than I do.
Wait a minute, let her say it.
And then there's always Google and Wikipedia.
This will be funny. The non-techie of the group.
TMDS over on en.wikipedia.org. Our fastest way to chase up buzzwords.
Okay, it's transition minimized differential signaling.
So
I believe
some
that
sort
it's-
of parallax something.
As defined by Wikipedia, it is a technology for transmitting high-speed serial data and is used by the DVI and HDMI video interfaces as well as other digital communication interfaces.
In other words, when Warren and I were talking about those hyper-modern, do people still use that old EDID stuff to detect how the monitors are doing? Well, many of them don't because they use this newer stuff. Hey, if I got a Spark and I've got a Radeon in it, then it does all this stuff. Well, not that it's very much stuff, but it does it anyway. Oh, darn, I have a Spark. I guess I have to use that EDID stuff.
Excuse me, Spark or PowerPC. They're both big Endian processors.
PPC_OF, so it's probably only some of the PPCs and not all of them.
That's what I was going to say. PPC can be either way. I think that you can set it on boot.
That is not true. PPC is big Endian only.
It is big Indian only? Okay.
It's MIPS that is.
Oh, is it MIPS is the one?
There's an old joke that some of the Sun people used to tease some people who base their systems on MIPS by calling it spin backwards. And the joke goes that they quietly abandoned that little witticism when
somebody realized what
MIPS people said,
Spark is
"If you keep
backwards."
that up, we'll start calling your architecture backwards.
Spin, MIPS. So there's some in-reg BIOS for Scratch. So in that particular construction, there would be some scratch space. Oh, there's this non-DDC laptop panel. Probe a secondary head. So this is the part where it's making all the decisions about exactly what kind of monitor need you have attached to this thing anyway, and what to do about it.
And it has to define this differently.
Even how, the important detail here is even how to actually ask for it is different from major processor architectures. Then in a few cases, if we got some information, we didn't get all of it, we have to sort of flip it around because not getting all of it, but getting a certain amount of it in a certain structure means that you're using one of the older types of structure.
Not getting in too far into the details, the PowerPC does support both Indiannesses, although it starts in Big Indian. It's a what?
That's a myth.
It's a myth?
Yes, it is actually not true. There is a Little Endian mode in PowerPC that is really Big Endian.
Okay, hold up. Repeat what you said.
You're going to have to explain maybe. The supposed ability of PowerPC to act as both Little Endian and Big Endian is a myth because there is a supposed Little Endian mode on PowerPC which is actually Big Endian. I don't understand that.
I was actually going to go into those details. I mean,
I'll let Warren explain.
Are you going to read this on Wikipedia?
I'm not going to read it, the whole thing. But I was going to say that it appears that only certain places in memory can actually be accessed in the Little Endian mode, and that according to this, it is, quote, enough to appear Little Endian, so which means that it's obviously fake.
It's a compatibility fudge in order to support certain kinds of drivers or pokes and peaks or something.
So without going too much down a rat hole, but just to clarify that, okay, yes, almost too late. It's calling it fake implies that it's completely dishonest, and it's not completely dishonest, okay? So you have a choice in architecture whether you want to have your instruction codes big Endian or Little Endian. You have a choice whether you want to have your data Big Endian or Little Endian, okay? Some architectures only support data that is Big Endian or Little Endian. The instructions are always in Big Endian, okay? And sometimes you take a performance penalty when you go to when you have a Big Endian processor and it does the Little Endian, because basically all of the stuff goes through the barrel shifter and gets swiped or gets swapped in a second instruction. But a lot of the times, if it's a superscalar out-of-order execution processor, you never see the delay unless you're doing something funky, okay? So I don't believe...
There might also be things at the scale of human senses at which there is a slowdown, but it doesn't matter to us.
Correct. So it's usually below the threshold of human perception when they do that, okay? So PA RISC had both data Big Endian, Little Endian, and it had instruction Big Endian and Little Endian, and in fact there's a very elaborate code sequence to go through that. You know, most of the processor architectures have said there's a huge amount of data that's available on Intel processors that's Little Endian. We have to be able to access that data, so they have some way of dealing with it. The Intel processor itself has a byte swap instruction, which is all about making 32-bit data Big Endian or Little Endian, and that was specifically put in to make networking code go faster. So, you know, you could call it fake, but as far as you're concerned, most people just don't care.
That's not what Warren was talking about.
I'm going to defer to the expert on this one.
Why don't the people who are interested in this particular aspect read the Wikipedia?
I'm going to move on within the framebuffer code, not diving into the PowerPC specific aspect of it. The note from the programmer here says that this next function applies to any architecture model or machine-specific fix-ups, which means that this is some stuff which is not going to care so much about the Endianness as some specific values that just have to be forced into some places in order to make things work, or to be fetched out of some places in order to get some information that it needs. Flat panels are pretty simple stuff, so it just does a few bit shifts and off it goes, basically. we've got a mode definition, and this is the kind of stuff where I started paying attention because I had my monitor spec sheet with all of those nifty little porch values and the exact frequencies I was messing with. And I had my mode lines that were successful when I was poking around with them, specifically because I was sort of playing blind from a serial interface. So I could install some values into what was being used here, only this is actually a function about the panel info, so this is supposed to be filled in from the EDID request. So I was still looking for what's the table it's filling it in from, or is it only able to get it by asking the monitor, and if the monitor can't answer, is it stuck? So video mode to var. There's some apps actually that allow you to create a frame buffer kind of mode line, but that's used by the console driver, and I wanted to see if I could get it filled in earlier. So we're still on the part where it's asking EDID about stuff. Is the panel info that it got valid? Looks okay, sure. Build the mode database from the EDID. I suppose if I was going to force it, I could kind of hack it here so that no matter what it got as EDID from the monitor, it would do what I told it to. We need to figure some, or we need to read it from the card. So now we're starting to get to something. I need to chase down where it was getting the mode database from. Oh, no, we can't find out what the panel size is. We're going to have to treat it just like one of those plain old boring televisions. We're just assuming a panel size. Too bad. We guessing. And setting a flag to say that we guessed, that it has a default mode that we gave it. But here, a pickup default, we could pass in a mode option. That, I think, is where it's honoring the command line where we can give it a mode command. Now, when I was looking at this stuff, I had been looking at a text file that described a little table of modes. And that table of modes was actually in a 2.4 kernel, so I'm not entirely sure the exact same table of modes would be correct for a 2.6 kernel. This is used when looking for modes. We assign a distant value to a mode in the database to see how close, based on the resolution.
Can we get line numbers on that, any chance?
Good question.
Set MU, if you're in VI.
I'm in less, actually.
Hit V. Hit
E.
V. Trust me, hit V.
I hit V.
What are you trying to do?
Now, set MU. Colon set MU. Not C, set. Thank you.
One of the few things that's actually rather difficult in Emacs and trivial in VI.
Yes!
VI versus Emac fans everywhere rejoice as line numbers show up out of nowhere.
Topic. VI versus Emacs.
So things like FBCon basically passes out current mode with XWES res hacked. Ooh, hacking the available resolution. That was the kind of thing I was looking for. Yep. While things like XFree will actually just produce a full timing that we should respect as much as possible. Darn. So the frame buffer console here is a part where they're setting up as much as they can, and all the stuff that doesn't get filled in, they're filling in with something so that they can use it. What if we got it from EDID? Great, use it. What if we only got some of it? Okay, do some checking and fill it in. There's that database. Go looking in it. If we have a scalar, we allow any mode from the database, and if we find something that matches that distance it was talking about above, close to the resolution that was being asked for, we'll just go ahead and use it. We just didn't get any sort of pick out of the database that was anything like what we were looking for. Fine, give up, whatever. Maybe they can't see anything in this mode. And return this kind of error code that it's an invalid call. I don't know how familiar anyone watching this will be with the fact that error codes all start with E for error, but basically that's the case. This is an invalid call. We didn't have a scalar we wanted. Tough luck. We lose. And if it's really that bad, you might find that even though it looked like it was going to be radion kind of stuff, that it was just about something it said on the box in one of the other frame buffers, so that it can get to showing you spiffy things like cute penguins and itty-bitty text instead of that horrible, huge 80 by 25, oh no, out of prehistory type text. And then get on with the visual life that we in userland are used to. My question for everyone here now is, who's interested in leading our next kernel study into whichever direction we'd like to dive into next?
Chirp, chirp.
I'm going to be gone for 3 weeks.
Was that chirp or crickets?
That was chirp, chirp.
Chirp, chirp. I'm going to be gone
Crickets
for
chirp.
the next 3 weeks, so I can't handle any of this.
Hold on.
First, I'm going to ask our kernel study guide coordinator, what's the date of the next meeting that we're doing these kernel studies?
January 15th.
January 15th.
So we have a little while. Yes.
Why are we meeting on the 8th?
Well, we're not meeting on New Year's Day.
Yes. The 8th would be the following week.
Might make it a little
Because
hard to
I have-
decide on New Year's Day who's going on the 8th. but-
Yes.
You're free to have a meeting on the 8th. I won't be here for it, but you're free to
I
have
thought
it.
it was to give people time to come back into town.
So I'm the coordinator. I can explain my rationale, or I could just say I'm the boss and that's it.
I'm sorry, you're going to need to take a vote from the membership for that one.
All right, so then at the next monthly meeting where we can have everybody there, we can have a membership, or we can just do it my way.
Can we make sure this vote is contortion compliant so that we're people running and
All right,
does that-
so
Bruce, you're being a self-parody at this point.
yes, you are, Bruce. So I said the 15th, and I have a general philosophy behind that, and that is I wanted to make sure that we're always triply redundant. And what that means is there are 3 people who will sort of take responsibility for this meeting scheduled for that meeting, okay? So I count our president as one of those. I count me as one of those. I count Warren as one of those. And then I sort of figure out that the speaker needs to be around there too. And the general idea is I believe that family comes first. So if you're driving on the way here, you get a phone call that mom's in the hospital, poof, you're gone. All right? And I also have the feeling that money comes first. So somebody's coming along and he says, I got this job. It pays $200 an hour. Poof, you're gone. Okay?
$200 an hour. Wow, I like that one.
So I view the, I've done a lot of high availability, reliability kind of work. And the rule is you need to have 3 people scheduled in order to make sure that an event happens. 3 responsible people have to take responsibility for an event. And so I looked at what was going on and I figured the 15th, the 8th might happen, but the 15th is the first date that is triply redundant.
That's fair. That's fair. Yeah, worst case, then the 15th I can pick up.
So if we have a redundant array of inexpensive speakers,
That was a brilliant joke.
Perfect.
then we might have a number of topics or a number of people who want to lead, or we might even be able to combine these combinations into something that might happen.
I would hope somebody comes out of the woodwork. Okay. If not, one of my interests in the kernel is to investigate the scheduler. And so, what are the I don't know if that's something we should jump into.
It has been suggested that the scheduler of processes that run would be an interesting place to investigate.
So, yeah, and I have some experience with actual task management stuff from other contexts, so it's it's just interesting.
If no one speaks up to it, we can have someone consider diving into that section and see who can be running and who can be sleeping and which processes actually get themselves some ticks assigned. That sounds good. I'll throw into the pot a section I'd like to see people dive into, whether I'm the one who dives into it or someone else is. I think that it would be fun and useful, even from a user land perspective, to explore how the magic sysrec key actually works. For those of you who aren't familiar with that one, if you have your kernel compiled in that fashion, then there is a special attention key that can secure the attention of the kernel itself, and then a very limited number of functions you might expect out of what I call sysadmin land, like rebooting or syncing the hard disks, are really available at the kernel level because the driver at a primitive level is supposed to be what's called eventually to do that anyway. It will give it its best shot, and that's what you get.
Keys, those things are off.
You still have to actually have it compiled in, though, and you have to have it activated if the kernel is compiled so that it's activated starting off.
What is it? Is the magic C? Is it alt sys request
But
S and then alt sys request?
exploring these things are for a later session, so at this point, I'd like
sync, unmount, and reboot.
I'd like to thank our audience for having some fun with this, and I'd like to thank Google for hosting us.
And I'd like to thank Heather for actually getting up there and speaking. I can't believe it. We're done before 9:30.